Hello, Calculus. You're viewing this on Tuesday, 9/13, sometime after class. And we are going to look a little more at the delta epsilon definition of the limit. So I'll call it that. Delta epsilon definition of the limit. All right, so you had your first shocking view of this yesterday. So I'll just do another example, use the terminology again, and just see if it's coming out a little more clear each time that you visit it. So let's say that we are looking at a function, and that function as x approaches a, so visualize a function, and as x approaches a, as we come in from the left and from the right at a, and we're picking various values of x, then that limit is L if for every absolute value of x minus a less than delta, so that is saying that our values for x are within delta away from a. And I'll draw that in a second. Then, if that's true, and the limit is L, then this will also be true. And we'll confirm that the limit is L, where the function minus L, the absolute value of that, is less than epsilon. For any epsilon, no matter how small. So this is saying that the function is with, the function is within epsilon of L. Let me show you that. This was all devised by a French mathematician named Cauchy, and he did this in the early 1800s, and it has stood the sands of time, stood against the sands of time, and is still used today. So you have him to thank. All right, so let me show you a little picture then. If we have, say this problem, the limit as x approaches 2 of 2x plus 3. So that function will look something like this, going through that point. And as x approaches 2, right here, so that's our a is 2 in this problem, then this function should approach 7. So graphically we have an idea of what we're looking at, and that is true if for every x, which is delta away from 2, so here we go 2 plus delta, and over here we have 2 minus delta. So we are establishing an interval around 2 where we go out delta in one direction and out delta the other, with 2 right in the middle. And if we choose those x values wisely, it will always get us in the target area between 7 plus epsilon and 7 minus epsilon, no matter how small epsilon is. So that is the kind of terms that we've been passing around to one another. If you would, write down this statement, and we'll go and prove, use a delta epsilon proof. Write down this statement. So I kind of put it in words on the board so you can copy it again, saying what we said yesterday, maybe in slightly different words that maybe you'll click. 7 is the limit of this problem that we're messing with. For every if, 7 is the limit if these things work out. For every epsilon I give you, you can find a rule expressing delta in terms of epsilon. So if I give you an epsilon, you're going to do something with it and call it delta. Say you're going to take epsilon and multiply it by 2, and that's your rule. Or maybe you're going to take epsilon and divide it by 3. Somehow you're going to mess with that epsilon and call it delta. For every epsilon I give you, you can find a rule expressing delta in terms of epsilon so that values which are within So the values within delta of x will target outputs from the function to be within epsilon of 7. This shouldn't be x. What should it be? In this case, where x is approaching 2. So that'll be specific for this case. So that values within delta of 2 will target outputs from the function to be within epsilon of 7. So, back over here to the picture. Maybe those words will clarify the picture, maybe the picture will clarify the words. So once again, 7 is the limit. If I give you an epsilon, no matter how small I give it to you, and you know that you can find a delta, which is some function of epsilon, that when you go to the left and right, delta of 2, it will guarantee that you are within epsilon of 7. If that's true, if you can find such a delta, then 7 is the limit. All right. Let's go ahead and do an example. Finish up this example. And here we are, and we're going to do the delta epsilon proof. Let's say that we're going to go to the meat. Here's the meat and potatoes right here. Is that showing up? Sorry, I have to keep checking. All right, so I'm going to say on my scratch paper, this is my scratch paper, I'm going to work backwards, and then I'll come over here and do the actual proof. So working backwards, I'm going to start at the end, and I'm going to say f of x, and in our case, f of x is right here, minus L, the limit, which we're saying is 7. So the absolute value of that is less than epsilon. So I'm going to work backwards and see what delta has to be. So over here, I will declare delta to be that and prove that this is the limit. So working backwards from this side, I'm going to say, I can express absolute value. Well, let me clean up. 2x plus 3 minus 7 is going to be 2x minus 4. And then an absolute value can hop out if we write it like this. A negative absolute value is less than 2x minus 4, which is less than, I don't need the absolute value anymore, which is less than epsilon. I'm going to factor out the 2. My goal is to get this to look like this. So in our problem, this problem is x minus 2. So I want this to say x minus 2. Right now it says 2x minus 4, but look how I can get it to say x minus 2. I factor out the 2, and I divide everything by 2. Alright, so now I have an exact match. So in my problem, this is going to be absolute value of x minus 2 is less than delta. And over here, the function 2x plus 3 minus 7, the limit has to be less than epsilon. So in the forward march part of the formula, part of the proof, I'm going to start with this and show this. But I don't know what to call delta, so I'm going to start with this and work backwards so that I can go forwards. Can you see in this box what is delta? Notice right here, this is saying x minus 2 is less than delta, and I've found that delta could be epsilon divided by 2. I can rewrite this back in form with the absolute value. Like that. So I have found a delta that works. If I give you any epsilon and you divide it in half, you will always get where you want to be within the limit. So let's do the proof straightforwardly. So on that side, put the scrap work away, and you're going to start with the correct side of the proof. If the absolute value of x minus 2 is less than delta, then we have to prove this. If it works out, then we know that 7 is the limit. So rewriting that without absolute value, negative delta is less than x minus 2, which is less than positive delta. I'm going to come in and multiply everything by 2. And then I'm going to distribute the 2 in the middle. And now I'm going to rewrite the minus 4 like I see here. Instead of, I'm going to call it plus 3 minus 7. Can I not do that? That's the same as minus 4. How did I know to do that? Because I kept my eye on the prize, what I want it to come out to be. But we have established that delta is equal to epsilon over 2. So I'm going to let delta equal epsilon over 2. Alright, so now I can establish minus epsilon is less than 2x plus 3. The 2's cancel. And I have minus epsilon is less than 2x plus 3 minus 7 is less than epsilon. And I can rewrite that in absolute value notation. And voila, that's what I needed to show. So therefore, 7, I'll put therefore, 7 is the limit. How do I know? Because no matter how small you make epsilon, you say I want to be within 0.0000001 of 7. Well then, I will easily do that. I'll say, okay, then delta has to be epsilon divided by 2. 0.01 divided by 2. And that will always get me within epsilon of 7. So that shows that 7 is the limit. Alright, so you'll be doing some of those eventually. I'm not sure where you are on your work list, but they are going to appear now. Notice how we work backwards and then we work forwards. So to satisfy the delta epsilon definition of a limit. All right, over and out.